Welcome to our Next Chapter Weekly group. We have William Yan from Duke University, and he's going to be talking to us about some drug metabolism and what happens after you take that pill and why somebody might react differently. Thank you so much, William.
Thank you, Mr. Well. Hi, everyone. My name is William. I'm a rising senior from Duke. And today we're looking at drug metabolism, and we're really answering this question of what happens after we take a pill. So there's three central goals to drug delivery is first we want to get the drug to the right place and at the right time and with the right amount. So example for that is with the right place, like there are inhalers for asthma patients to deliver medicine precisely to their lungs. And with the right time, there are tablets that kind of slowly release the drug over several hours. And an example I can think of is like an anti-cough medicine called Mucinex. I think it's a pretty common one. It has a green layer on the top that's like very fast at dissolving, and there's like a white layer at the bottom that kind of slowly release and give you that long-term protection of the anti-cough effect. With the right amount, for example, like insulin dosage for um, diabetes patients are very carefully calculated on the body size and age. So then take a look at the journey of a medicine. So first, the drug enters. After we ingest the drug, it gets into our gut, into our intestine, and then it gets absorbed by the bloodstream from the intestine. And then after it gets into the bloodstream, the blood circulates, and then the drug spreads around the body. And then finally, for the metabolism, it's mainly where the liver plays a very big role here. When these blood that's carrying these drugs get into the liver, the liver basically modifies drug to have a lot of functions, which I am going to touch on later, and that's going to be the focus of our presentation today. And last but not least, like we don't want the drug to be in our body for so long because having anything too long in our body, especially drugs, is going to have very serious side effects. So we're going to process that and then allow it to leave our body. Okay, so first of all, that's the absorption process. So first, like the stomach acid is going to dissolve the pills, and then these drugs are going to be better absorbed into the blood vessels, and then um, yeah, and they will interact with food. So uh, there are times where medicine will be recommended to take without eating anything, or there are medicines that's recommended actually like to take it with breakfast or with a meal. And the reason for that is because food interact with the medicine. So first of all, food will kind of signal our stomach to, hey, it's time to digest something, and it enhances the blood flow into our GI system, which is increase the blood flow to the intestine and helps with the overall absorption. And another thing that the food does is that it slows down the stomach empty, kind of having something that blocks the pill from dropping too fast. So there's more time for us to dissolve the pill and absorb them. And another thing is if the drug is like a fat soluble one, it can be dissolved in fatty food. And for this one, always drug label and a physician instruction will always give a pretty clear idea about these food interactions. Okay, and then the second thing and the focus of the presentation today is the metabolism and with how the liver plays a role in the drug processing. So after absorption, the drug goes into our liver to be modified. And the reason why we want to modify drug is there are many reasons. Is one of them is the activation. So for some of the drugs, we don't want them to be active all the time. So only after we get it into our body, getting processed by the liver, we then want to activate it. Um, there's also times where we want a slow activation. For example, like the case I gave for Mucinex, we want an extended period of protection. Another thing that liver does with metabolism is they modify the drug to detoxify them. So, for example, like a very common drug like Tylenol, which is also known as acetaminophen, can be toxic if overdosed, but the liver will kind of take care of this process by detoxifying them. And then another thing is there are drugs that's fast soluble. So some drugs has to be fast soluble because only with that property it can reach a specific target in our body. But the thing with fast soluble is that we cannot, excrete it out. Like our urine is water soluble, and essentially we don't want this fast soluble drug to be in our body for so long before it um, gives us side effects. So the liver also will attach some, alcohol groups or other modifications that make these fast soluble drugs actually soluble in water, and then it can be excreted by our kidney system. So that leads us to a very important enzyme, or I should say an enzyme family called CYP450. So it is a very large family of liver enzyme. There's over 50 kinds of them, and it helps to break down or modify painkillers, antidepressant, blood thinners, and birth control pills. And as you see on the right, that's a very beautiful structure of the enzyme. And in the middle, we can see there's a group called a heme group, and it is actually a very similar group that's on our blood. And at the center of that, this brown thing is the iron, which I will talk about in the next slide. So this central iron atom, what it does is it carries the oxygen with it, and it adds what we call in chemistry OH, or alcohol group, to the drug. And what this does is we know that OH is like soluble in water. So now, this enzyme, a big part of its function is to convert a fat-soluble drug into a water-soluble drug, so we can easily excrete it and then, detoxify it. Okay, and next, we're going to move on to explain like why are there differential effect of medicine? Because some people might metabolize the drug faster, right? Sorry, slower. And then this would mean that the drug will stay longer in our body, which has more potential for side effects. And for the fast metabolizers, the drug actually leaves very quickly. So immediately when we take the drug, like we just excrete it out. Then that means we probably want a bigger dose of those drugs. So a good example of that is the older population generally has a slower metabolism, so kind of excrete it and absorb it in a slower pace, which means that the drug is going to stay in us in a long time. So that's why a general practice in medicine is to give lesser dosage for the older population. Okay, so talking about CYP 450, what are some common disease when it is being dysfunction, given that it's such an important enzyme? There's some genetic variations of the enzyme that gives poor drug metabolism. So for example, a specific enzyme called CYP2D6, which is in the CYP450 family. And the dysfunction of that leads to traditional painkillers not working because this specific enzyme activate a chemical called codeine to morphine. And basically, morphine is the natural painkillers um, that inhibits the sensation of pain in our body. And then if there's a genetic variation that cause a rapid metabolizer, for example, with the ultra-active CYP450, that can lead to excreting drugs too fast, and that significantly reduces the drug efficacy. And another thing to CYP450, if not genetic or environmental, it could be the damage to the liver or liver disease will reduce the CYP450 enzyme levels. So without a healthy liver, we cannot express that many enzymes, and that will also affect the ability to process drugs. Okay, so for the last slide, I just want to leave it on a little fun note on the question of why can we not take alcohol with drug when normally not recommended. I think when I was a kid, I was very confused when my grandparents told me that, oh, you cannot drink too much alcohol because otherwise you'll get toxic effects from the drug. And really, the reason behind that is the liver also process alcohol. And by processing two at the same time, by processing both alcohol and the drug, that kind of overloads the liver. And liver is like our attention. Like it can only focus on one thing and do it well at one time. And short-term effect of that is alcohol can actually interact with the CYP450 and then inhibit them. So slowing down this enzyme metabolism. And this, again, kind of tying back to the overall theme, if we modify it slower, that means it takes longer to get out of our body, which means that the drug accumulates and leads to toxicity. So this is a short-term effect. And if there's a chronic alcohol consumption, then um, then our body kind of adapts. So our body first will have this effect of oh, having a lack of metabolism, but then our body compensates for that by producing more CYP450 enzymes. And then when we're not drinking alcohol and then taking the drug only, that will lead to ultra fast metabolism that kind of deems the drug a little bit useless by reducing their efficacy too much because when we immediately take the drug, it got immediately out of our body as we overcompensate for that. So with that, thank you for listening, and I will take any questions after the recording is stopped.
Great. Thank you so much, William. Yeah, that was very interesting. And we always ask our Duke University students to give us the right terminology because we want to learn what's going on. And so we can better talk to our doctors or whatever. So you can always go back and listen to this again. So.